Hello everyone. Today we will discuss about what is a bridge, comparison between DC and AC bridge, basic Wheatstone bridge circuit, balance conditions, passive bridge circuit example, and conclusion. Bridge is a special electrical circuit consisting four arms, four nodes arranged in a particular manner. Bridge basically used for resistance, inductance, and capacitance measurement. Bridge circuit in its simplest form consists four resistances arms. A source of current is applied to two opposite junctions and a current detector is applied to two another junctions. The bridge circuit use the comparison measurement method and operate on null indication method. Bridge circuit compares the value of an unknown component to an accurately known standard component. In bridge circuit, when no current flows, the galvanometer shows zero deflection. The bridge circuit is said to be balanced. The relationship between the component of the four arms of the bridge at the balancing is called balancing equations. Bridges are basically two parts, DC bridge and AC bridge. DC bridge. DC bridge works on DC supply and have zero frequency. Only resistance are measured. Phasors are not involved because there is not any frequency. Used for measurement of resistance only, used for measurement of current and voltage, where we cannot use ammeter and voltmeter. Basic examples are Wheatstone bridge and Canville double bridge. AC bridge has AC supply can be measured, RLC, phasors are involved, power factor, dissipation factor, Q factor, loss factor can be measured, used for measuring of RLC. Basic examples are Maxwell bridge, Anderson bridge, Hayes bridge, and Van bridge. The circuit shows a basic Wheatstone bridge circuit. Wheatstone bridge, invented by a scientist, Charles Wheatstone in 1833. Series parallel combination of four resistance gives zero deflection voltage in balanced condition. The bridge consists of four resistance with source EMF and a null detector. Arm consists resistance R1 and R2 called ratio arms. Arm consists the standard resistance R3 is called standard arm and the arm which consists R4 and R4 is an unknown resistance which is to be measured. The battery is connected between A and C while galvanometer is connected between B and D. Battery and galvanometer are always connected on the opposite nodes. This is the balance condition for a basic Wheatstone bridge. Galvanometer does not show any deflection. If potential across B and D, point B and D are same, then galvanometer shows zero deflection. From the circuit, we can easily write I1R1 is equal to I2R4. As galvanometer current is zero, then we can easily say I1 is equal to I3 and I2 is equal to I4. Considering the battery path under balance condition, we can easily calculate I1 is equal to I3 is equal to E divided by R1 plus R2 and I2 is equal to I4 is equal to E divided by R3 plus R4. By using above equation and by putting the values of I1, I3 and I2, I4 in above equation, we can easily calculate the balance condition which is R4 is equal to R3 multiplied by R1 divided by R2. Following points can be observed. It depends on the ratio of R1 and R2. Then these arms are called the ratio arms. As it work on null deflection, the results are not dependent on the calibration and characteristics of galvanometer. The standard resistance R3 can be varied to obtain the required balance. For understanding the basic Wheatstone bridge, we can take a example of a example of a simple circuit in which a 12-volt battery is connected across a 10 ohm and 20 ohm resistance which are connected in series. We can easily calculate the value of current by KVL, and the value of current is I is equal to 0.4. The voltage across 10 ohm is 4 volt and the voltage across 20 ohm is 8 volt. Now if we connect another 10 ohm and 20 ohm resistance in parallel with the previous 10 ohm 20 ohm resistance, then we can also calculate current. Current remains in both the arms same 0.4 ampere and 0.4 ampere. The current which is extracted from the source is increased because the total impedance is reduced by the parallel combination. Now connecting, the voltage will also remain same. Now we can calculate the potential VAB. For calculating the potential, we can easily look to the ground from the point where we have to calculate the potential. So potential at A is 8 volt and potential at B, VB is 8 volt. So potential difference VAB is equal to VA minus VB, which is 0 volt. Now we can easily say that this condition is a valence condition. Now we take another example of circuit in which we reverse the position of the resistances 20 ohm and 10 ohm, where VA is now 8 volt and VB is now 4 volt. Then if we calculate the potential difference VAB, then it is 4 volt. Now we can easily say that the deflection will not be zero, and the galvanometer which shows a some amount of current. So this circuit is unbalanced circuit. Now finally we can conclude by changing values of elements connected in the circuit we can obtain the balance condition. Mechanical balancing always done by balancing mass or force. Similarly, as mass and force are analogous to electrical voltage, so we can do electrical balancing by balancing voltage. We can find the value of VAB either theoretically by KVL and KCL or by connecting an equipment that can measure basic quantities like voltage, current, voltmeter, ammeter and galvanometer.